So good morning, and thanks, Kelly, for this wonderful conference. I have to say I'm a computational scientist, and early on in my career I was heavily influenced by theories of machine learning, and I feel bad about the fact that it's harder and harder to find conferences that actually brings computational scientists with people who think hard about the theory behind this kind of computation. So I very much enjoy conferences like this. Today I'm going to talk about optimal policies for value-based decision making. So as you can tell from the title, we're talking about optimal policies, so hopefully it fits fairly nicely in the overall theme of this workshop. Though I need to warn you that, again, I'm a neuroscientist, so I'm interested in how humans behave and the neural mechanisms that are responsible for our behavior. So whenever you have this kind of constraint in your work, you have to massively simplify the kind of problem you look at. So here we're going to be looking at optimal policies, but it's a very, very simple type of situation, and Ron made a similar point yesterday. Okay, so let me start by first telling you that this work really was done by these two guys who were two of the fantastic postdocs in my lab, Sato Tajima, who's actually still in the lab, and Jan Drugovic, who just recently moved on to start his own lab. So we're looking at value-based decision-making, which is a particular type of decisions where basically you're giving options like this, and you have to pick one, but there is no objectively right answer. You have to base your decision on whatever is your subjective preference. Obviously, we make choices like this absolutely all the time. Whenever you enter a shop, whenever you go to restaurants, you constantly have to make this kind of choices. And what's interesting is that it's been argued extensively in the literature that humans are massively suboptimal for this kind of thing. There are many arguments that have been offered. The one I heard about a couple of years ago from Carlos Brody, who's one of the leaders right now in the study of decision-making and the neuroscience of decision-making, was pointing out something which is that whenever you're confronted with two equally high-valued items, stuff that you really want, typically people take forever to decide. I'm sure you've all experienced this. You go to restaurants, there are two items that you really want, the result is always the same. You're going to agonize over your decision, you're going to take forever to figure out which one to pick. And yet that makes little sense, right? Why should you spend a long time deciding between two options that are good? No matter which one you pick, it's going to be good. So I was listening to this, and then suddenly realized, like, yeah, that makes sense. On the other hand, I don't know what is the optimal policy for value-based decision-making. So we looked at the literature, and to our delight, I have to say, it's low-hanging fruit. Nobody had derived the optimal policy for such decisions. So we figured, let's start from scratch. So we're going to start with a kind of a classical starting point for these kind of problems. We're going to assume that the items that you're considering have a true reward, but the subjects do not know what the true rewards are. Instead, what they get is over time, say every 100 milliseconds or so, the brain generates a sample of value which comes from a Gaussian distribution centered at the true value of the items. And you get a long series of sequence of samples like this. Now, where are these samples coming from? I'd be happy to speculate about this towards the end of the talk if you're interested. Obviously, you're accessing your memory. You have to look back at your experience about ice creams and how much you value them. This process is presumably noisy. It's hard to recover those memories. The memories themselves may not be accurate. And so here it's formalized with a simple kind of sampling process from a Gaussian distribution. So we have a sequence of samples from one of the options, and we're going to assume that, of course, you have another sequence of samples in black for the other option. And now you have two basic questions that you may want to answer. One is, given these samples, what can you infer about the rewards of the different items? And second, when should you stop collecting samples and then decide? Classic problems of decision making. With the first question, given the samples, what can you infer about the rewards? It's quite simple in this case. We're just drawing samples from a Gaussian distribution, so you can just like derive analytically the posterior distributions over the rewards given the samples. Very easy, and when you do it, you quickly realize that the sum of the momentary evidence is a sufficient statistic for this posterior distribution. In other words, you don't need to keep track of all the samples. All you have to do is you take the sum of all the red samples, the sum of all the black samples, and that's all you need to know to figure out the posterior distribution. Okay, so we just have to sum samples. Another question is, when do you stop? How do you stop? It's a stopping rule. If you look at the literature, you'll find that there are really two extremes of models that people have used in literature. It's really two extremes of a continuum. You can easily actually go from one to the other, and they're known as race model or drift diffusion models. It's a pretty simple concept. With race models, the idea is you have two accumulators. So you have two different accumulators that are going to sum the evidence for, in this case, ice cream and chocolate cake. And so you have those two races that drift upward, because in this case we're going to assume that both items have high value on average. And you have a threshold. And whenever you hit the threshold, you stop. The time it takes you to get the threshold is going to be your reaction time, and the race that hit the threshold first determines which option you're going to pick. On the other extreme, you have drift diffusion models. In drift diffusion models, you only have one accumulator, and the accumulator takes the sum of the momentary value of the ice cream minus the chocolate. So it takes the difference in values between the two items, it sums this over time, and now we have two bounds. And so the process diffuses, and when you hit one of the bounds, you stop, that's your reaction time, and the identity of the bound you hit determines your choice. Pretty simple. And you can already, see that with this process here, if you have two equally high-valued items, the difference is going to be tiny, so the drift of the diffusion process here is going to be near zero, and it's going to take a very long time to make a decision. So that will explain right away this observation that we have a hard time with equally high-valued items. So indeed, if you think about the decision speed for those models, in this case it's determined by value. The higher the value, the faster you're going to drift toward the bound, whereas here it's determined by value difference, and so it's going to take forever the values are similar. So if you think about it, it looks like race models appears to be really the sensible approach to value-based decision making. When you're dealing with good options, it will guarantee that you decide quickly. On the other hand, the data seems to be consistent with drift diffusion models. Okay, so as I said, there's actually a variety of arguments that have been offered in the literature for why value-based decision making is actually suboptimal, and I'm just going to review some of them that are particularly relevant for the kind of models that I'm going to describe later on in the talk. So first of all, we get slow reaction time for equally good choices. Second, humans in value-based decision making tend to violate the principle of independence of irrelevant alternatives. So what is this? This refers to the following situation. Say I give you two choices like those ones. They're supposed to be high-value choices. I actually was confronted literally with those choices a few months ago, going to this restaurant in Reims, and they offered me for the appetizer either this asparagus broth with asparagus and caviar, or the other option was some foie gras that was wrapped into a jelly of ponzu sauce, which is a Japanese vinaigrette. And I can tell you that I resolved my problem here by ordering both, so I know that both are fantastic. But say you have to decide, that you're forced to choose. Now what's bizarre is that your ability to choose between those two things is influenced by whether you have a third option available or not. And what's even more bizarre is that it's influenced even if the third option is something that you're very unlikely to pick. So I lived in Rochester for many years, and in Rochester the culinary specialty is this thing. It's literally called a garbage plate. I'm not making this up. I think it's unedible unless you're really drunk and it's 4 in the morning, which is the only time I tried it. And it tastes just the way it looks. So confronted with those three choices, at least for me, I'm very unlikely to pick this. And yet the data shows clearly that if you have these choices available, then it's going to be even harder to decide between the two top options. Which again seems kind of bizarre. Why would an irrelevant alternative influence your choices? Third fact that is puzzling is the fact that people have noticed that there's a normalization taking place in the brain between neurons encoding value. So this came out of Paul Dimsch's lab, who has been recording some cells in a part of the brain known as LIP, where we think that neurons are sensitive to value. We think that because if you record from a neurons whose receptive field here is shown in gray, and you record the response to a target that's associated with a particular amount of reward, how many spikes you get from that neurons depends on how much reward is associated with that target. The more reward, the higher the response typically. But that's not the end of the story. What they realized is that how much neuron responds to this target actually depends on the amount of reward that's available outside the receptive field. Now keep in mind that if you were to present those targets alone, without that one, you would get no response from that neurons because you have nothing in the receptive field. But what they noticed is that the response to 2 drops of water here is influenced by how much reward is available out there. And the relationship is such that as you increase the amount of reward in the periphery, then the response drops. So this is again the response to 2 drops of water, right? So there's some kind of normalization response. How many spikes you get here depends on what's going on in the periphery. So why is this the case? Not exactly clear. I should mention that this kind of normalization responses have been found throughout cortex. In fact, it's been found in insects. There seems to be a nonlinearity that you find in almost any neural circuits, and typically thought to be related to game control. So it's very helpful, for instance, if you step out from this room, you go outside, the light intensity is going to go up by many orders of magnitude. If you don't do something about your circuits, you're going to saturate all your circuits. gain normalization can actually make sure that you stay within the dynamic range of your neurons. But here, we're nowhere near saturating the response to the neurons. Why would you have such a nonlinearity? A fourth fact that's kind of puzzling is also that people find urgency signals in the brain. So this comes from the work of Churchman, Coyote, and Shannon, who have been recording from neurons in the same area, LIP, while animals are forming decisions, and found that if you look at all the neurons at once, you see that all of them, during the decisions, their activity go up together, regardless of their preference for the different options. This is kind of the common signals that just rise, that make the activity of the neurons rise toward the threshold. What's also puzzling about this results is that where this urgency signal starts, so the offset here, depends on how many options are available on the screen. So this is summarized here. Typically, the offset here is higher when you have 2 options versus 4. And for those of you who are actually used to Mike Shannon's work, you recognize this kind of traces. This is a ramping activity that's related to evidence accumulation. And you can see in those traces that indeed, typically, neurons respond more for 2 choices here than they do for 4 choices. Okay, so there are urgency signals. And then there's also Hicks Law. And Hicks Law is a psychological law that has established that typically reaction times are proportional to the log of the number of choices that are available to the subject. Now, for the information theory people, you'd be happy with the generalization of that. It's logged to the entropy of your choices if your choices are not equally probable. So it looks like there is some interesting kind of search algorithms that's running in the brain during such decisions. And whatever models you develop have to be able to account for this. So the question I want to address is really, so is value-based decision making suboptimal? And there is only one way to know, of course. We need to go back to square one and try to figure out what is the optimal policy. So the task we're going to look at is we're going to imagine that you're subjected to a sequence of such binary choices. So you get many of those choices. And your goal is going to be to maximize your reward rate. So how do you maximize your reward rate is the question. So we imagine in every trial, we're going to draw the value of the 2 items that we're going to have to choose from prior distributions, which we're going to assume to be Gaussian distributions. And then, of course, we don't get to see the true rewards. We get to instead see samples that are collected, that are sampled from a Gaussian distribution centered at the true values. And as I mentioned earlier, the first step is you need to do evidence integration, which is you just need to sum the samples. So we're going to represent the state of our system in this plot here. We've got accumulated evidence for option 1 and the same for option 2. And by summing the sample over time, we get this diffusion process. And the state of my system is just going to be characterized by the position of this particle in that 2-dimensional space. I think the people who are familiar with this literature already know where I'm going with this in order to get the optimal policy. This is simple enough that we can just open any textbook on this kind of issues. And we can solve, in this case, Bellman equation using dynamic programming. And so the idea here is that for every position of the particle here, we can assign a value function, which is the max of 3 different rewards, which correspond to the 3 different actions that you can take at any given time step. You can either choose to stop, pick option 1, and that's going to be the expected reward for option 1, given that you're in state x of t. You could do the same for option 2, or you could decide that you're not stopping, you're going to accumulate for 1 more time step, and that's going to be the value, the expected value, given that you accumulate for 1 more time step, and that you were in state x of t, and you're transitioning into state x of t plus delta t. So it's pretty easy to solve for this, and what's going to happen at the end of the day is you're going to have a value function that tells you which one of those actions is the best action for any position of the particles. So you're going to effectively partition your space into 3 different regions. And depending on which region you are, it tells you which option is the most valuable one. So there'll be a region associated with option 2, another one with option 1, and one that's associated with accumulation. Now, the only question really of interest here is how does this partition look like? Does it look like this, or does it look like that? There are other options that are possible. In case you're wondering, for instance, this particular partition here would correspond to an independent race model. Well, it turns out, once you go through this, is that it's this particular partition that's optimal. There's actually one more twist, which is that, So what happened is that at the beginning of a trial, you start here 0, 0, you start diffusing, and then if you hit this bound, you stop and you choose option 1, and this bound, you choose the other option. So as I said, there's an extra twist, which is that over time, the two boundaries here come closer to one another. They collapse into one another. So this may be obvious to most of you already, but this is effectively a drift diffusion model. You can reduce that to a drift diffusion model. It's a 2D diffusion process, but in fact, only one dimension matters, right? Because how much you can prove that those lines here are parallel to the unity line. So how much you diffuse along the unity line is irrelevant as far as your decision is concerned. All that matters is how much you diffuse along this axis here, which is a relative value axis, which is the difference in values between the two options. So it's really intrinsically a 1D diffusion process. So you can summarize it with a DDM in which you're now accumulating the difference in the accumulated evidence, the difference in the momentary evidence, sorry. And because the two boundaries here come closer to one another, in the drift diffusion model, your stopping bound has to collapse over time. So that was kind of the first big surprise. I mean, I didn't think this was going to be the optimal solution. I was quite convinced when we started the project that we were going to find that independent races is the way to go with value-based decision making. But once you work it out, it turned out DDM is the optimal policy. And therefore, the fact that it takes forever, whenever you're confronted with equally high-valued option, is actually exactly what you would expect from the optimal policy. However, the actual value of your option does matter, and reaction time should be sensitive, but it should be sensitive to the average value that you're getting. So if, for instance, you live in a world in which the value of your item is picked from this blue distribution here, which on average is not very good, so you live in a world where you're not getting that many rewards, you can show that this policy predicts that you should collapse your bound slowly. If you switch to the red distributions, where on average most of the rewards are high, then it turns out you have to collapse your bound quickly. And in between you get all possible collapses. So in other words, if you live in a world in which everything is good, don't waste any time deciding, decide very quickly, which makes sense. If it's the opposite, you're in a world in which most rewards are not that good, then take your time to deliberate. That's what this policy tells you. Okay, so you might wonder at this point, so how come race model is really not the optimal policy? So again, you could just look at the dynamic programming solution. But here's at least one intuition that maybe can make you help you realize that it's a bit more complicated than it looks at first. So I pointed out that if you have two good choices with a race model, then you decide very quickly. You've got fast reaction time. And I'm calling this hard choices because effectively it's hard to tell which one is the best. Right? Whereas with diffusion models, in this kind of situation, you're going to be slow. But for easy choices, that is a situation in which it's very clear that one option is better than the other, then you have an opposite pattern. For race model here, if only one choice is good and the other one isn't, then it's actually going to take longer to decide in this case than it took in the case where you have two good choices. It's kind of ironic that it should be easier to decide here, but with race model it takes longer. Whereas with drift diffusion models, since they diffuse according to a difference, if the difference is big, then you diffuse quickly toward the bounds. So they're better in that respect. So if you plot decision time as a function of choice difficulty, you find that with diffusion models, the easier the task, the faster you go. Whereas with race model, you get the opposite patterns. So now it's less obvious which one is going to be the best. And again, at the end of the day, it's the diffusion models that are best. In fact, we can quantify that in the particular situation I'm looking at. Race models collect only 50% less reward than drift diffusion models on average. All right, I want to go back to this issue of the collapsing bound. So there's a prediction that comes out of this, and we haven't done the experiments, and we love to do an experiment to test this. But what it says is that if I put the subject in a block of trials in which rewards are bad, on average, it should take a long time to decide. Whereas if I now switch them to a block of trials where you have lots of good rewards, they should start becoming faster, right? So higher reward rates should be associated with short reaction times. So fortunately, we run into a poster that's still unpublished, I have to say, by Otto and Daw. Many of you know Nathaniel Daw at Princeton, where they actually have data that already seems to support this prediction. The experiment was not designed at all with our theory in mind. They didn't know we were doing this work. But in this experiment, what they do is, at the beginning of each trial, they draw the reward associated with this trial from some Gaussian distribution. And the subjects are told here, okay, you're going to get 39 cents if you respond correctly here, otherwise 0. The task here is you have two sets of dots and you have to determine which one has more dots. Then you respond, and if you get it right, you get the reward. Otherwise, you get 0. And just because there's stochasticity in this process, if you look at the accumulated reward in a sliding time window of about 20 trials, and you plot this, you see that subjects have period of time in which they're not getting that many reward, and others where they're doing very well. And according to the theory I was just showing you, the reaction time should track that. They should be faster when they have lots of good rewards, and slower when they are in a kind of low reward phase. And so what those guys did is they regressed this average reward over time against reaction time, and they found that indeed the two are negatively correlated, which is exactly what we predicted. Now it's not a huge effect. This experiment again was not designed to test this, but I was quite surprised that humans can adapt so quickly on such a fast time scale according to their reward rates. Also, okay, so to summarize with two choices, what I've been showing is that drift diffusion models are indeed the optimal policy for value-based decision making. Being slow for two equally high value choices is not suboptimal. However, and that's important, reaction times do depend on how much reward you get, but they depend really on the average reward rate, not on just the reward on a particular trial. So this is all for two choices, but how about generalization to more than two choices? In fact, what I just described so far, we've just published a paper that came out recently, and then we're now trying to figure out how to deal with this kind of situations. This is actually all cat food. Just for cat food alone, there's definitely beyond two choices. Okay, so here, how are we going to handle this? So I guess one option would be, let's go back to the race model. So what would a race model look like with three choices? So we imagine that we have sample for the three options, and we're just going to sum them, and we're going to keep track of the position of our three accumulator in this cube here, and we get this diffusion process. And with the race model, the way you stop is you have thresholds on each of those races, the same threshold on those races, and effectively what it means is whenever you hit the side of this cube, you stop, and which side you hit determines your choice. So is that going to be optimal? You can imagine that it wasn't optimal for two choices. It's not going to be optimal for three or more choices. But again, we have to start from scratch. As far as we can tell, nobody had derived the optimal policy in this case. Again, we want an optimal decision rule, which is going to be the combination of evidence accumulation followed by a stopping rule. Evidence accumulation is just as before. Given a set of sample delta x, which is a series of samples here, we want to derive the posterior distribution over the reward. Exactly as before, the sufficient statistics is just a sum of the samples for each of the races, so that's all we need to keep track of. So in other words, for the first stage, which is inferring the posterior distribution, all we need to do is take the sum, which is this diffusion process, which is the same than what we were doing with the race model. So far, it's like a race model. How about the stopping rule? The stopping rule, we use exactly the same approach as before. Now we have a value function which is a max of n plus 1 terms. The first n terms correspond to picking, stopping the accumulation, and choosing one of the else options. So this is the average reward associated with the ice option, given that you're in state x of t. And the last one is the value associated with accumulating one more time step. So you solve for this, and again, you partition your space in n plus 1 different zones.
So the reward you get when you select a choice, that depends on some assumption about the underlying distribution, or because the state, you could be in the same state with different true rewards. So R hat, your R hat is a...
It's determined by it's the average, so you look at your posterior distribution and you just get the expected reward.
So you have a right, you started by saying that the distribution of underlying rewards from which these choices are being made.
Yeah, so I'm assuming that I know everything about the generative process, right? I know the prior distribution and I know how my samples are generated.
The cost is determining how fast the borders collapse, or where does this cost come from?
The cost of time, this one?
Yeah.
That's the cost of time. So this is lost opportunities, right? While you're accumulating the evidence, you're not collecting rewards. So you pay the cost of that.
Set by you? Or
it sets, sorry, the previous equation you had it has two terms. One is your average reward rate, right? Every time step you're not collecting rewards, you're losing the average reward rate, so there's minus something that's proportional to the reward rate. And the second term is actually that we have in there is a cost of time itself. That's a debate in the literature as to whether time has a cost. We have a paper with Jan Dugovic on this showing that some of the human data that we have seems to suggest that yes, you pay a price for just time. Could probably be due to
Yes,
effort,
sir.
cognitive effort, right? Probably paying attention. It's sure that when you run the experiments, they tell you there's nothing more dreadful than being a subject in the experiment. So you pay. Okay, so I said it's defining different regions, and so we cannot solve this analytically, by the way, which is kind of a bummer. Somebody can solve that for us. We'll be really happy. Right now, we're using brute force and solving this whole thing numerically. And here are the boundaries that we get in the case of 3 choices. So it's way more complicated. They're not inside of the cube, so the stopping bounds depend on the combination, on the nonlinear combination of your 3 accumulators. But you basically diffuse them there, and whenever you hit this bound, you choose. There's one property, though, that we can prove, which is that those boundaries are parallel to the unity line here, to this diagonal here. So what it tells us that, again, diffusion along these lines is irrelevant. All that matters is diffusion in the hyperplane that's orthogonal to the unity line. So in fact, we can project this diffusion process into this plane. In the 3D case, it's just a plane. And we're just looking now at a diffusion in this n-1 dimensional space in which the stopping boundaries are still nonlinear. And it turned out that the boundaries also needs to collapse over time, just as before, for the optimal pose. Okay, so is that too complex to implement with neurons? It's definitely not like a simple standard race model. It's a bit more complicated than this. We need evidence accumulation. We need an n-1 dimensional projections, right, onto that hyperplane here. We need non-linearities, because the decision boundaries are nonlinear. And we need collapsing boundaries. It looks complicated, but it turns out that it's actually not that hard to implement with neurons. So here's how we're going to approximate it. It's just an approximation. But we're going to start with accumulators and explain the reasons to believe that neural circuits are able to accumulate evidence. Then we're going to have a projection that we implement by having normalization terms. So we take the sum, the average activity that comes out of all those neurons, and we subtract it to all the neurons. We also have a nonlinearity here, so the activation function here is a polynomial, rectified polynomial function, which has some free parameters. We want at the end of the day to have a simple stopping rule, so we're going to basically impose on the system that you have an independent fixed boundary in each of those races, so each of them just look at whether they hit the threshold or not, and that's done locally. And we need collapsing boundaries, so we're going to get that by adding an urgency signal, by having all the neurons go up together according to some signal that forces them to go toward the threshold, which is the same as collapsing the threshold. It's just done the other way around. And the question is, can you get this to approximate the optimal solution? There are a bunch of free parameters. You can play with the offset of the urgency signal, its slope. The polynomial function can be adjusted, the height of the threshold, and so on. There are about 4, I think, free parameters. So we optimize those parameters. And at the end, we look at what kind of bound they optimize, and we compare to the optimal bounds. So you see here, dotted line is the what we get from the network, and the solid line is the optimal one. And so we get very close approximation to the optimal values. Yeah.
Are the bounds of the circuit also parallel to the diagonal?
I don't know for sure. What I know that in this case we hit the maximum reward rate. So they have to in a sense, but I haven't really checked. Okay, so there are quite a few now components in this model. How important are they? So what we're going to do here is we're going to plot the reward rate as a function of the number of options. It's a relative reward rate, so we're going to plot everything compared to the full model here, okay, with all the different components. So if you remove the urgency signal, you pay a little price. It's not that big, but you do a little worse if you don't have the urgency signal. If you remove the normalization, but you keep the urgency signal, you pay a much bigger price, which really indicate that this particular step here is really critical. And if you remove both, then you start really paying a heavy price. In fact, it's more than the sum of those two things. So there's some kind of nonlinear interactions between all the different components. So for optimal performance, you really need the normalization and the urgency together. Okay, so let's go back to the urgency signal now. So we've optimized our system, we have an urgency signal. We can start comparing it to what has been found in vivo by Mike Shadden and collaborators. And remember, it takes this shape. I'm going to spare you the details about how exactly they extract the signal. It's actually somewhat involved. But we pretended that this was just a piece of brain and used the same strategies they used. What we find is that the urgency signal has roughly the same profile. But what we were wondering about is, how about the offset? So I mentioned that the offset depends on the number of options. It's smaller for 4 options than it is for 2. And it turned out, so, which you can see in the traces, but it turned out that we have exactly the same thing coming out of the model. I have have to warn you, most of this work is quite recent, like over the last 6 months, so we don't have explanation for everything. I cannot yet explain exactly why is it that the optimal solution has this property, but it matches what has been found in the neurophysiology. How about the normalization? So remember that in the brain, how much a neuron responds to a target associated with, say, 2 drops of water goes down as you increase the amount of reward that's available in the periphery. We get the exact same effects in the model. In the model, it's completely obvious. It comes from this particular normalization here. But what looked like a strange result here comes from the fact that we needed to have this projection onto this n-1 dimensional space. And so this is the consequence of that projection. So going back now to the violation of the independence of irrelevant alternatives, I need now to explain to you briefly how this is technically quantified. So this is data from, again, the Paul Dimsch's lab, in which they asked people to choose between option A and option B. And they here plotted how many times you choose, say, option A as a function of the difference in values between the 2 options. And what happened is as you increase option A relative to option B, you picked option A all the times and vice versa. So this is called a psychometric curve. And what they found is that as you introduce a third target, the psychometric curve is becoming more and more shallow, right? As you increase the value of the third target, even if you never pick that third target. So this is what they call this violation of the IIA, as they call it. It's getting harder and harder to choose between A and B in the presence of C. And we get exactly the same effect in our network. This is, again, a consequence of having the normalization. The different choices have to interact with one another. They're not independent anymore. Finally, Hicks Law. So that's another one of those results I was just discussing with Matej and Daniel, where, frankly, I cannot tell you yet why we get it, but we were kind of surprised to see that you get this logarithmic relationship. So this is log 2, by the way. So log of the number of options, the reaction time as a function of the log of the number of options. We find that whether we're doing a perceptual task or a value-based task with our model, we get a linear relationship.
So the 2 is irrelevant.
What?
The log 2 is irrelevant.
The log 2 is irrelevant, but I mean, it's often explained by saying that what people do is they divide into the set and then they redivide into...
It depends on the dimension of time.
Well, so there is no unit in this case, yes. But the point is that it's actually interesting to see that this kind of systems, which was definitely not designed to divide into the number of options in sequence, nonetheless actually exhibit behavior that's very similar to this kind of systems. So the big, I think, message of this whole work is that normalization, which seems very ad hoc, might actually be optimal. This is one of my favorite models of the last 10 years on value-based decision-making that come from Tim Barron's lab, where they studied how people decide between 3 different options. And in this model, they have those lateral interaction between the neurons. There is a competition going on. And the reason they have it is because otherwise they simply cannot fit the data that they have. But there is no explanation as to why it's there. And they're not only allowed to do this, except they say, well, we know the neurons do that, so let's just have it in the model. So here I'm saying that, well, it may not be just a hardware constraint. This actually be biology exploiting this particular nonlinearity to achieve near optimal performance. So to conclude, I started by showing you that DDM implements the optimal policy for value-based decision-making. However, it's really important for this policy that the collapse of the bound is related to the prior distribution of the rewards. The more reward you get, the faster you collapse the bound. Then we saw that you can generalize this to the ND case, where you have this complex bound, but fortunately, you can implement or you can approximate this optimal strategy with a very simple neural network that has many of the components that are found in the brain. Thank you very much.